So in the last lecture, we had finished discussing about what does the actions of the discrete time LTI system mean in terms of the frequencies and what does it do to the input frequencies. Okay. We'll finish that discussion by pointing out that just like in the case of continuous time LTI systems, discrete time LTI systems are given certain names based upon what kind of frequency response they have. So some of the discrete time LTI systems, or as they are called filters, have special names, discrete time LTI systems. So remember, one of the basic continuous time LTI systems or filters is a low-pass filter. There is a similar notion of a low-pass filter in the discrete time. So there is, the first example is a low-pass filter. Now, in the discrete time, the low-pass filter is defined as, in the continuous time, the low-pass filter is defined as any filter that keeps all the frequencies up to a certain point and kills the rest of the frequencies. In the discrete time world, we have to be careful with that definition because of the fact that discrete time frequencies are only unique from minus pi to pi. Okay? So a low-pass filter in discrete time filter, a low-pass filter, it has a Fourier transform h of e to the j omega. If its magnitude response, and will primarily be concerned with the magnitude response. So a discrete time LTI filter whose magnitude response is 1 or maybe another constant between plus omega c and minus omega c, and all of this is between minus pi and plus pi. Okay. But because of the periodicity, you have the same thing repeating after. So you have the same thing happening around 2 pi and minus 2 pi and so forth. So this point will be, for example, 2 pi plus omega c. This point will be 2 pi minus omega c. Okay. So omega c, just like in the continuous filters, omega c is called the cutoff frequency. So it's a similar concept, but the cutoff frequency has to be strictly less than pi. And typically, it will be around like pi by 2 or so forth, and it will be called a low-pass filter. Okay? If it goes above pi, then actually it has to be a constant because of the periodicity. Similar to then the concept of high-pass filter, there is a high-pass filter in discrete time. Again, the definition we'll give is in terms of the magnitude response. The magnitude response of a high-pass filter in discrete time. Now, if you remember, in continuous time, a high-pass filter it starts at some point. Its response starts at certain point omega c and keeps on going up to infinity for 1. You can't have that notion in the case of the discrete world because, again, the periodicity. So the high-pass filter in discrete time looks like it is this rectangular response around minus pi and pi. So it keeps high frequencies. Remember, frequencies which are around pi are high frequencies in the discrete world. It keeps those, and then it has to have the same periodic structure. Ideally, we will say that all of these magnitudes is 1, but it can be something more than 1. So the same thing will repeat then at 3 pi and at minus 3 pi and so forth. So the low pass and high pass filter, it's really that where is this rectangular region of the frequency response situated in the discrete world. If it's around 0, those are low frequencies. It will be around 0, around 2 pi, around 4 pi, and so forth. If it is around pi, then it will be around minus pi, minus 3 pi, 3 pi, and so forth, and then it will be a high pass filter. Okay. Similarly, we talked about other cases of filters. The two more common ones are band pass filter, which basically lets a certain region in your frequencies pass without any damping and kills all the other frequencies. Once again, the response that looks like is the following. So the band pass filter basically picks a band between 0 and pi, and it lets those frequencies go by and kills all the others. Okay? But the same thing then has to be repeated at multiples of 2 pi. Okay? So you will have the same thing happening here, you will have the same thing happening here. Okay. And the last example is that of band stop filter, which is just the reverse of band pass filter. So band stop filter is that it lets all the frequencies pass except a certain region. So that band stop filter will look like. And there will be periodic repetition of that. Okay, so it's if you think of from minus pi to pi, which are the really main range of frequencies in discrete time, it lets all the frequencies go except these frequencies between this region. Okay, so all these filters are defined. In the high pass case, there is only one parameter, omega c. In the band pass case, there is omega c1, omega c2, minus omega c1, minus omega c2. And in the band stop, you have similar version. This is omega c2, omega c1, minus omega c1, and this is minus omega c1. And this is minus omega c2. So this concludes our discussion of introduction to the discrete time frequencies and understanding how the discrete time LTI systems act in the frequency domain. Okay. So if you now combine this knowledge with your linear systems class knowledge, we understand the meaning of frequencies in continuous time. We understand the meaning of frequencies in discrete time. We understand continuous time LTI systems and discrete time LTI systems both in time domain and in frequency domain. Okay? But the missing piece that we haven't talked about is what is the interface between these two worlds? Right? If I have a continuous signal like my voice, how do you take that continuous signal and convert it into a discrete signal, and what does it mean to do operations on my voice if it's now in the discrete domain? So we needed all this this mathematical foundations to be able to answer those questions. And now what we want to do is talk about really the interface between the continuous world and the discrete world, which is obtained through sampling theory. So sampling theory effectively helps us bridge the continuous and the discrete world. So informally speaking, the word sampling simply means the process by which continuous time signals get converted to discrete time signals. Now there are many different types of samplings, but we can only touch upon the most commonly used type of sampling, which is called uniform pointwise sampling. That will be the focus of our class. Okay. So what does uniform pointwise sampling mean? Let's try to understand this word. So uniform means that every few, so it could be micro, milli, or any other prefix, every few seconds, it's the same operation that you are doing every few seconds. Okay, it's uniform. You do it at, let's say, t equal to 1 second, then you do the same operation at t equal to 3 seconds, t equal to 5 seconds, and so forth. Okay, so that's the uniform aspect. The pointwise aspect is that you find out what the signal is at a given point in time. So pictorially, what uniform pointwise sampling, and going forward, I won't make the distinction that it's uniform pointwise sampling versus sampling. I'll just call it sampling. Okay? What this does is it actually, whatever is the signal, it is a mechanism. How you do it in hardware, we are not going to talk too much about that. But what it does is it goes to the signal every few milli or microseconds and asks what is the value of that signal. So if you are recording my speech, what sampling does is every few microseconds, it basically says what is the fluctuation in my speech, what is the value of my speech at this time. Okay? If you're recording it through a microphone, then you simply ask what is the current or voltage associated with that, with the speech at that particular time. So if you are given a discrete, if you are given a continuous time signal, let's say this is your signal, what uniform pointwise sampling does, let's say this is time 0, okay? It basically asks what is the signal value at t equal to 0, and then it asks that same question again after t, capital T seconds. Okay, so it asks at t equal to capital T, it asks at t equal to 2t, t equal to 3t, And it would have asked the same thing even in the past. So t equal to minus t, t equal to minus 2t, t equal to minus 3t. Okay. So this kind of sampling, the only variable that you have is when do you take the sample? When do you find out what the value of your signal is? And that is the variable capital T. So this is called sampling with time period capital T seconds. Okay. And what you do is, whatever is the value of the function or signal at those instances of time, you record them into a sequence. And that's the way you obtain the discrete version of the signal. So what you get is, let's say you have a signal, let's call the signal GA of t. Okay. You construct a sequence GN, which is simply asking what is the value of the signal at GA0, GA T, capital T, GA minus capital T, just like this. So it computes this value for 0, plus minus 1, plus minus 2, and so forth. Okay. So for example, this value, whatever is this value, this is G of 0. And this value is G of 1. Similarly, this value is G of minus 1. Okay. So you read those values and you put them into a sequence. In the terminology of sampling theory, this T is called sampling period. Sometimes you are said, here is the sampling period. Sometimes you are given the sampling frequency, and that is simply 1 over t. So if you compute 1 over t, that is in hertz, or you could be given sampling frequency in radians per second, which is often written as omega of t. Sometimes people put the subscript capital T to signify that it is related to the sampling. So capital T is 2 pi f. T equals 2 pi over t radians per second. Okay. So if you, for example, look at the songs that you are listening on your MP3, oftentimes you would, for example, read, it talks about the sampling rate of that song is 44.1 kilohertz. Okay. What that is referring to is that how the song was converted from the continuous world to the discrete samples was by taking its samples at a rate of 44.1 kilohertz, which means you are taking 44,100 samples per second. Okay? Or every 1 over 44,100 seconds, you are taking a new sample. So pretty much every digital signal that you see, you will see associated with it a sampling rate, most often given in terms of hertz. So converting the continuous signal to the discrete signal is actually very easy using this uniform pointwise sampling. You just go read the signal value, put it in a sequence. The challenge is the following. How do you know that what you have recorded is enough to represent the signal? For example, should I sample, if you are sampling my voice, right, should you sample it every 1 second, every 100 milliseconds, every 100 microseconds, right? That's an important question, because the continuous time signal, it consists of infinite values. And you have replaced all of those values with just a discrete sequence. If you take back this example, between time capital t equal to 0 and t equal to capital T, you have this function fluctuating, right? You have this curve that is going, but you have not recorded those values. What should be your time duration, your sampling, so that you can really recover all of these missing pieces of information? You are listening to your music. How do you know that the music you have recorded can reproduce the same music that you recorded? Okay. So the main aspects of sampling theory are about answering the following questions. Under what conditions on, first of all, the signal GA of t and the sampling time, or maybe frequency, or omega, you can be given any one, is sampling a process that loses no information. The question of whether you will lose information or not is really a function of what type of signal you have. So sampling theory is always about, for this class of signals, this is how you should sample. Okay? And so that is the question of, for example, recording. If you again take the example of just speech or music, that is the question of recording. How should I record a signal? How should I digitize a signal so that I don't lose any information? So now, let's say you were in a music studio and you recorded the signal because you understood that question. The second question is, you have recorded it, your goal is to play it back. All you have is a bunch of numbers, zeros and ones. How do you play them back so that it sounds exactly like what you started with? So the other part of sampling theory is how to recover the continuous signal GA of t from its samples G of n. Sampling theory is really about, in general, both these questions, and they are intertwined. Right? For a certain class of signals, you have to use certain types of reconstruction operations to reconstruct the signal. Now, being an elementary class, we will actually fix the conditions on the continuous time signal. So in this class, conditions on GA of t will be that it is a band-limited continuous time signal. Okay. So we'll fix that condition, and if we fix that condition, the only condition that we need to then address is what is the condition on my sampling time so that I don't lose any information. So let's first though understand the meaning of band-limited signal. A band-limited signal is a signal in which there are no frequencies present in the signal above, let's say, omega p radians per second, or equivalently fp hertz. Okay? So a signal in which there is no frequency, higher frequency present after a certain limit is called a band-limited signal. So omega p is the highest frequency in GA of t. And since frequencies tell us the rate at which a signal fluctuates, if we know the highest frequency in the signal, what do we know? So highest frequency in GAT, it tells effectively tells us the highest rate of fluctuations in the signal. Again, you can be given that in either radians per second or hertz. So band limited to, mathematically what band limited signal means is, since we know that all the information about frequencies is given to us through a mathematical transform. What's the name of that transform? Fourier transform. So band limited to omega p radians per second mathematically means that the Fourier transform of G, let's call it GA J omega, okay? This transform is equal to 0 for all omega bigger than omega p. Because if the Fourier transform had any non-zero value after omega p, then that means the signal has frequencies higher than omega p. So omega p is called the bandwidth of the signal GA of t. So figuring out whether the signal is band limited or not is as simple as just looking at the Fourier transform of the signal and seeing whether it becomes 0 after a certain range or not. So an example will be, now remember we are talking about now continuous signals, which means continuous Fourier transforms. So let's say I had a signal whose Fourier transform magnitude was, let's call it 3 and 2 pi 10 to the 3 minus 2 pi 10 to the 3 omega. So this signal, is it band limited or not? It's band limited because it becomes 0 after 2 pi 10 to the 3 radians per second. So the bandwidth of this signal in hertz is 1 kilohertz. So this signal has a bandwidth of 1 kilohertz bandwidth signal. On the other hand, if I had a signal whose Fourier transform looked like this, then this is not a band limited signal. We assume that it's continuing. Maybe it hits 0, but it never stays 0. Okay. So band limited doesn't say that the signal can't, within its frequencies, it can't hit 0. The idea is there is no limit to the highest frequency that is contained in it. Okay. So a signal like this, or even a signal like this, stays 0 and then become non-zero. It's Fourier transform. Okay. Both of these classes of signals, whether you talk about the red one or the black one. Both of these are non-band limited signals. They don't have any frequency above which their Fourier transform becomes zero, or from an engineering perspective, their rate of fluctuation is not limited at a certain range. They keep on fluctuating at arbitrary rates. So this is not band limited signals. Another type, which is really what you see in the practical world, is something like this. Don't focus, by the way, on the shapes that I am drawing. It is the notion of band limited signal is not contained in the shape. Okay, so don't focus on the shape. It's where they hit zero or whether they hit zero or not. Do they stay zero or not? So what you technically see is something like this. In the real world, what happens in the real world is that there is no such thing as a band limited signal. Okay, and the mathematical reason for that, if you remember your duality theory from linear systems class, is that if something is band limited, if something has a Fourier transform which is zero after a certain limit, then the signal must go on forever in time. Now, if I am speaking, I can't keep on speaking forever. So just saying that means I can't have a band limited signal. But the real world, what happens is that while you have frequencies that keep on going after a certain range, most of those frequencies are very small contribution. Okay. Here and here. This is again the Fourier transform. So in the real world, what happens is we don't have perfect band limited signals, but we have signals that we can say are approximately band limited. About this is the range, you will say this is the effective bandwidth of the signal. So in reality, we have these kinds of signals. For developing theory, what we are forced to work with is perfectly band limited signals. So when I say for theoretical purposes band limited, it means that the signal has no higher frequency above a certain range. So the main thing that we'll study in this class is that if signals are band limited, then what you should really think of is that the signals can't fluctuate beyond a certain range. And if that is the case, then they can be sampled or converted or digitized, whatever term you want to use, without any loss of information. The focus here is loss of information. You can always sample a continuous signal, but you don't want to lose information. And then the only variable that we have access to, if I have fixed my signal, I have fixed the kind of sampling I do, which is uniform pointwise, then the only variable that we have left is how fast should we sample. And the answer to that depends upon the bandwidth of the signal. You can ask yourself heuristically though, what happens if a signal has higher frequencies present in it, which means its bandwidth is high, do we need to sample them more often or less often? If a signal has higher bandwidth, then that means they have high frequencies, which means they are fluctuating faster. That means that to prevent loss of information, you should sample them more often so that you don't lose any information between two samples. If a signal has a smaller bandwidth, then the sampling requirements go down. How often you have to sample go down. And in sampling theory, we will precisely develop what should be the rate of that, what should be the value of that sampling time, or equivalently, the sampling frequency. So here are some examples of band-limited signals in the real world. We are studying band-limited signals because many signals in the real world can be approximated as band-limited signals. And one of the classical examples of that is voice or speech. So if you think about it, voice is the same thing when you are listening to it in person, but when you are trying to digitize voice, the question that comes up is, what are you using it for? So based upon a lot of analysis and its old story, that most of the intelligibility in human voice, okay, and I'm talking about intelligibility, not melody, okay, most of the intelligibility in human voice is contained up to 3.4 kilohertz. So while the voice that I'm emitting, human voice that I'm emitting, it can go from very small frequencies up to 20 kilohertz. Most of the intelligibility is just contained in 3.4 kilohertz. So if your purpose is to just talk to someone over the phone, you can treat voice as band limited to 3.4 kilohertz. In reality, how do you do that? You use a filter before you do the sampling, and we'll study that later. Before you do the sampling, you actually throw out all the frequencies about 3.4 kilohertz. So this is what the plot shows, that if you are thinking of transmission over the telephone line, okay, it's called POTS, the acronym for plain old telephone service, it's 3.4 kilohertz, okay? And you have to sample it at a certain rate to satisfy that. Now, if you want to talk about what is called HD voice preserves some of the higher frequencies, which is where, for example, melodies lie. So, for example, it's a really bad idea to try to compete on American Idol by singing on the phone, okay? And the reason is that you will lose all of your high frequencies if you try to do that, right? And that is one of the reasons you know someone in person and you talk to them over the phone and you say, you sound different on the phone, right? Because you have thrown away some of their frequencies. HD voice preserves frequencies up to 7 kilohertz. Okay, so if you are using voice for for better sounding purposes, you treat it as a band limited signal of 7 kilohertz, and you use a filter to throw out everything above 7 kilohertz before sampling, and you effectively now have a band limited signal. The reality of, if you want to preserve everything, all the music that you are playing, all the sound that you are capturing, then your voice should really be treated as band limited to 20 kilohertz. Okay? This is what's sometimes called full HD voice. Right? What it is saying is you are preserving everything in the voice that you can possibly make sense of. Another example of, so this is just voice signals. Another example of a signal which you can think of it as band limited is ECG signal. Okay, which looks like this. Now, long time ago, this ECG used to be analog, continuous time. But now you get to have digital ECG monitors, and by that they mean they need to sample it. Okay? And this signal, if you really think of it, and people have done analysis, in most cases, not all, in most cases, ECG signals have a 150 hertz bandwidth. Okay? They are really low frequency signals. There isn't that much fluctuation, just 150 hertz bandwidth. Okay? A third type of signal is, for example, if you work with seismologists, they will like to record these earth movements using, again, if you have seen those, at least Hollywood movies in which they show this needle sort of moving around, right? Traditionally, that is used to be an analog process, but you can digitize that. Now you have digital seismometers that record the earth movements, but if you want to record that, you better know how fast does that signal wiggle so that you can sample it. So traditionally what is assumed is that seismic traces or seismic data have a bandwidth of 125 hertz, not kilohertz, just 125 hertz. So these are some of the examples of signals that are band limited, but the real world is full of signals that you can approximate as band limited, and then you can apply sampling theory to them. Okay? Now, there is no mathematical table for telling you what is the bandwidth of the signal. That requires engineering understanding or talking to people who do applications and saying, based upon my analysis, it seems that a model for this signal to be band limited between up to this frequency is the right model. So we are going to work with band limited signals, but the idea is that the bandwidth of a signal can be 10 kilohertz, 100 kilohertz, a megahertz, a gigahertz, and you have to select your capital T appropriately so that you don't lose information. And one way of intuitively thinking about why you can lose information is, it's a hand-wavy argument, but you can draw some intuition. The continuous time frequencies range from minus infinity to infinity. Right? Or on the positive side, a frequency can be, as I said, a gigahertz or a terahertz or so forth. There is no limit to that. On the other hand, discrete time frequencies suffer from this non-uniqueness after minus pi to pi. So effectively, they range from minus pi to pi. So you're packing everything that existed from minus infinity to infinity into minus pi to pi, and there is some inherent loss of information because of that if you are not careful. Okay? So for a fixed T, the idea in sampling is that if I fix my capital T or my sampling frequency, there are certain band limited signals that I can use, but there are other band limited signals that I cannot use for sampling. So if I design a system that samples voice for example, just communication over the phone line, I can't use the same sampling time for a system which is to be used in a music studio. Okay? And to illustrate this notion of ambiguity, when you go from continuous time to discrete time, so there is always an ambiguity associated with going from continuous to discrete, and to illustrate that, we really should look at the building blocks of Fourier transform. Right? Because all that we are talking about is frequency, so let's talk about a particular frequency. So take the example, which is example 2.5 in your text. We'll take three signals which are just pure sinusoids. So the first is cosine of 6 pi t. This is a sinusoid of 3 hertz frequency. The second one is G2t, is cosine of 14 pi t. So this is a sinusoid of 7 hertz. And let's take the example of G3 of t, which is cosine of 26 pi t. So this is a 13 hertz frequency. And now let's say that we will sample this every 0.1 seconds. So let us generate discrete time signals by sampling every 0.1 seconds. So t is 0.1, which implies that my frequency is 10 hertz. Okay, my sampling frequency. So I'm going to sample 10 samples every second. Okay, so let's do that. Is just plugging in the value. So G1n is simply G1 of nt, which is cosine of 6 pi n capital T, and then I'll plug in the value of capital T, so I get cosine of 0.6 pi n. So this is a discrete now sinusoid. So I've sampled a continuous sinusoid to get a discrete sinusoid with a frequency of omega naught equal to 0.6 pi. Okay, so that's good. Now let's sample the second one with the same time duration. If you do that, you'll get cosine of 14 pi n capital T equals cosine of 1.4 pi n. Okay, so this looks like a discrete sinusoid omega naught of frequency 1.4 pi. But what do we notice here? So this omega naught is 1.4 pi, but this does not belong in the range of minus pi to pi, which means there is a frequency between minus pi and pi which is the same as this omega naught 1.4 pi. And how do you get to that? Actually, omega naught is effectively 2 pi minus 1.4 pi, which is equal to 0.6 pi. Okay. So this is the same as cosine of 0.6 pi n. Okay. Just the property of cosine, right? 1.4 pi n is the same as 0.6 pi n. Let's do this now with G3n. Cosine of 26 pi n t equals cosine of 2.6 pi n. This means that this is a sinusoid with frequency 2.6 pi. Now again, this frequency does not belong to the principal range, which means there is another frequency that it corresponds to. How do you compute that? You just subtract 2 pi from it, which means that omega naught equals 2.6 pi minus 2 pi equals 0.6 pi. So this is the same as cosine of 0.6 pi n. So what do we see here? We started with three distinct continuous time cosines which had frequencies of 3 hertz and 6 hertz, 7 hertz. So we had 3 hertz, 7 hertz, and 13 hertz frequencies. We sampled them with 10 hertz. And what do we get back in the discrete world? The same signal. So if someone were to show me the samples alone, someone were to show, here are the samples, I have no way of knowing whether I started with a 3 hertz sinusoid, a 7 hertz sinusoid, or a 13 hertz sinusoid. And the only safe guess I can make is, let's assume, and that is the right guess because of the theory we'll develop, is let's go with the smallest sinusoid because if that was the original sinusoid, then there's no way we could have gotten another one. Okay? So this example demonstrates the notion of ambiguity that is always associated when you are sampling continuous time. So this is a graphical representation of the same phenomenon. The three frequencies, the three cosines of different frequencies are shown in this plot with using different colors. Okay? And the green ones are where you take the samples. So you are taking the samples, and as you see, these samples are part of all three sinusoids. Okay? That's the ambiguity part, that because you are sampling at such a low rate, you can't tell if this sample is coming from the 3 hertz frequency or the 7 hertz or the 13 hertz one. Okay? So if I just look at, look at samples, then the right approach is to assume 3 hertz frequency. Okay. And this is the phenomenon that appears, it's very common in sampling theory, where something which is higher frequency appears as lower frequency when you sample it. So we looked at the signal of 13 hertz, it appears as a 3 hertz signal. Okay? And this phenomenon has a name called aliasing. So just like an alias means taking another name, aliasing means high frequencies take up the name identity of lower frequencies. We'll study more about aliasing later in the lecture. So the discrete frequencies, if you remember, right? Discrete frequencies do go from minus infinity to infinity, but the only unique part is contained between minus pi and pi. So there is a wraparound of frequencies that happens. Minus pi, pi, okay? Now, this whole region is then repeated again and again. So you have the same region repeated here, up to 3 pi, okay? So if you have a frequency here, right, between pi and 2 pi, that is actually a frequency between minus pi and 0. If you have a frequency between 2 pi and 3 pi, that is actually a frequency between 0 and pi. Okay? So you just have a repetition of that same thing on the right side, and you can keep on repeating the same thing on the left side. So far we have talked about the need to understand when does this ambiguity arise. We have said we are going to focus on band-limited signals. Now, sampling theory for band-limited signals will start addressing that. And physically, how you do it is different, but you can write it at least in terms of block diagram. This is a diagram that you often see, T equal to NTGN. What it means is you can think of it that the way you sample your signal is a signal is coming in and there is a switch which closes every capital T seconds. So in the previous case, it closes every 0.1 seconds. You measure what the value is and you store it in the sequence. That's the diagram you see. Another block diagram that you see is this kind, where you see the word CD, which is continuous to discrete, and there is capital T listed on the block, which means that is the time, the sampling time. So you get GN. Sometimes you get also a diagram like GA of T. Sometimes just people write ADC on it with T and GN. So you can be given different figures. They all mean the same thing, what we talked about, that you're measuring your signal every 3 seconds. ADC is the most closely related to the physical quantity. In physical world, what you use for sampling is called analog to digital converter. So ADC is an abbreviation for that. And all of the analog to digital converter chips basically come with prescribed sampling frequencies for them. So you will hear like this is a 1 megahertz ADC or a 1 kilohertz ADC and so forth. Now, we are interested in finding out when does GN preserve information in GA of T. Okay. So if we are going to ask when does the time domain signal preserve information from the time domain sampling, we can equivalently ask the same question in frequency domain. Because remember the analogy of this being two sides of the same coin, I can equivalently ask the question, if I define the Fourier transform of Gn as g of e to the j omega, and I define the Fourier transform of this as Ga of j capital omega, then I can ask the question, when does g of e to the j omega preserve information in Ga of j omega? Okay. And we'll really be studying sampling theory from this perspective. Now, we can write down the definition. So the definition of Ga of j omega we know is simply minus infinity to infinity Ga of t e to the j omega minus omega t d omega. Similarly, for the discrete time Fourier transform, it is g of e to the j omega equals summation n from minus infinity to infinity g of n e to the minus j omega n. Now these are the definitions of the Fourier transform, and if we just stare at them, well, the most we can do is I can replace Gn with its exact value, which is Ga of nt. Right? That's the definition of the discrete sequence. But even if I stare at these two equations, it seems hard to be able to tell what is the relationship between the discrete time Fourier transform of the samples of a signal and the continuous time Fourier transform of the original signal. Okay? We want to establish that relationship. We want to say under these conditions we don't lose information, but it is hard to draw that conclusion by looking at this formulation. So what we will do effectively is actually play a little mathematical trick, not do that in terms of physical systems, but we play this mathematical trick that we say this block which converts the continuous system to discrete system, we are going to write it in two steps. We are going to say replace that with the following. We get GA of t, and then we first multiply that GA of t with another continuous signal, which is called P of t, which is a periodic impulse train. So it is defined as n from minus infinity to infinity delta of t minus nt. So it's a combination of impulses every capital T seconds, and the output I define as Gp of t. Okay. As we will see later, this thing just appears as if we are sampling our continuous signal using Dirac impulses. This is still a continuous time signal. And then we put another block whose job it is to convert to sequence this Gp of t. And we get Gn. Okay. The input-output relation of these two pictures stays the same. We start with GAT, and when I write down all the details of this, you will see that this Gn will still be defined as Ga of nt. So the input-output relationship of these two blocks will stay the same, but by writing it in terms of these two different blocks, we will be able to simplify our analysis and be able to really explain the relationship between the discrete time Fourier transform of Gn and the continuous time Fourier transform of GAT. Okay? So that will be our goal in the next class.